How would life be beyond the stars? How would it be to live in a future where humanity has overcome all its problems and spread throughout the Milky Way? Think about it. Trillions of people living in harmony, from the galactic center to the farthest spiral arm. One day, a mysterious message arrives from another galaxy, another intelligence. Imagine the excitement at discovering that we are not alone. Ideas begin to be exchanged, and science, art, and philosophy flourish. Then, a bold plan arises. Two great civilizations from different parts of the universe decide to meet. Two ships finally approach in the vast and dark intergalactic space, and then, the long-awaited moment. Two emissaries float in the void, extend their hands, and disappear in a blinding flash. The ships pull back, stunned. They discover that one civilization is made of matter and the other of antimatter. Any contact leads to total annihilation. How did they not realize this before? They shared science, mathematics, engineering. How did something so fundamental go unnoticed? The laws of the universe are mysterious and complex, and often it is difficult to unravel all their nuances. From the immense to the minuscule, these laws are what shaped our universe in the first billionth of a second after the Big Bang. And at the heart of it all, there is a crucial concept: symmetry. Everyone has a basic idea of symmetry, like a mirror reflection from left to right. Our faces and bodies are symmetrical, one right eye with a left eye, one left arm with a right arm. But what happens when the rules of symmetry are broken? Like the fiddler crab, with one oversized claw, which looks like it has a personal trainer just for that claw. But symmetry goes beyond reflection. A starfish, for example, uses rotational symmetry. You rotate it, and it looks the same. A millipede uses translational symmetry, repeating identical segments. And it is through these symmetries that nature is economical in design. Did you know that symmetry can even evoke a profound emotional response? In our idea of beauty, facial symmetry is pleasing, though inside we can be quite asymmetrical. This appreciation for symmetry is reflected in art and design. Ancient temples in Egypt and Greece, the Taj Mahal, the Arc de Triomphe, and artworks like Da Vinci's Last Supper. Rotational symmetry is powerful, present in pre-Columbian discs, Islamic patterns in mosques, and even the Pentagon, the headquarters of the US Department of Defense. But you may be wondering, how does all this relate to the fundamental rules of the universe? In 1832, the mathematician Évariste Galois brought many new ideas to mathematics, and central to them was symmetry. The mathematics of symmetry was not new. Ancient geometers knew that a rotating circle remained the same. Triangles, squares, and pentagons also look the same after rotations. But Galois went further. He focused on algebra, specifically on polynomials. Polynomials are equations with quantities raised to powers, squares, cubes, and higher. He wanted to know if there was an algebraic formula to solve all polynomials, but instead of finding this formula, he proved that it did not exist. Instead of struggling with algebra, he looked at the symmetries of the solutions. He saw that the solutions to polynomials were complex numbers, points on the complex plane. These points formed shapes that could be reflected or rotated. It was a radical way of doing mathematics, translating equations into geometric images and thinking about their symmetries. Since his work in the early 19th century, insights about symmetries have emerged in group theory. Modern cryptography relies on this theory, but it is the impact of symmetry on science that is most surprising. And as he died, Galois did not know that his scribbles would revolutionize our understanding of the universe. Here on Earth, electrons move and form the radio beam that carries our messages. But on the other side, in the aliens' instruments, it was positrons, also known as anti-electrons, that moved. Electromagnetism has a fundamental symmetry. Swap all positive charges for negatives and vice versa, and the result will be the same. On May 1, 1935, Albert Einstein wrote about Emmy Noether, describing her as the most significant creative mathematical genius the world had ever produced. Einstein highlighted that Noether's insights were essential for a deeper understanding of the laws of nature. But what did he mean by that? Noether's theorem is all about symmetry. The main point is simple. The universe, nature itself, is lazy. That's right, lazy. Nature always chooses the easiest path, the path of least resistance. With the advent of modern science, mathematics began to replace mysticism, and geometric symmetries emerged from the equations. Newton's gravity created spherical planets and stars, while the magnetic fields of electric currents presented themselves in cylindrical shapes. These symmetries were pleasing to the eye, but hid something much deeper. Let's meet two big names in this story: Joseph Louis Lagrange and William Rowan Hamilton. Lagrange, an Italian who lived during the French Revolution, helped introduce the metric system. Hamilton, an Irish prodigy, came almost a century later. Despite their differences, they shared a vision: to reformulate Newton's equations. Pierre de Fermat had already proposed that light always chooses the fastest path in an optical system. Imagine driving home during a storm. You see a shorter path, but full of traffic and traffic lights, and another longer path, but with less traffic. Which is the fastest way to get home? Fermat realized that light makes the same calculation. It always chooses the path of least time. Lagrange and Hamilton extended this idea to all of physics, discovering that nature always chooses the laziest option. Emmy Noether realized that if equations have symmetries, there are special quantities that do not change. Think about the conservation of energy. Energy cannot be created or destroyed, only transformed. This idea applies to many other quantities in physics, all conserved thanks to symmetries. Imagine an experiment on a table. You push the table and redo the experiment. The result is the same, right? This shows translational symmetry, which implies the conservation of linear momentum. And if we perform the experiment tomorrow, the result will be the same as today, resulting in the conservation of energy. Noether showed that all conserved quantities in the universe are linked to underlying symmetries. In quantum mechanics, for example, probability waves have symmetries that result in the conservation of electric charge. Symmetries also predict fundamental forces, such as the strong nuclear force that holds protons and neutrons together. So, when physicists study interactions in the Large Hadron Collider, quantum conservation laws prevail. Almost all fundamental interactions are linked to these laws, symmetries and conservation laws operating together. Everything in balance. In the 20th century, while some astronomers focused on contact with extraterrestrials, others were grappling with something even more fundamental: the existence of antimatter beings. And it all revolved around a seemingly simple problem: how to distinguish left from right. It may seem silly, but explaining left and right to an alien is more complicated than it sounds. You can't send a picture because they would need to know the difference between left and right to understand. You can't use cultural references, like writing, because they wouldn't have that background. You need to appeal to something written into the universe itself, something that breaks symmetry. And that's where the concept of parity comes in. In 1956, scientist Chen-Shung Wu was observing cobalt atoms spinning in a magnetic field, expecting to see a symmetrical distribution of electrons being emitted. She noticed that all the electrons seemed to escape from one side of the atom. This meant that the radioactive decay of cobalt was not symmetrical. This was related to the concept of parity. Until then, it was believed that the conservation of parity was a fundamental law of physics. It was as if the universe seen through a mirror was as real as our own. But Wu's discovery showed that the weak nuclear force, responsible for certain types of radioactive decay, did not respect this symmetry. The violation of parity by the weak force was just the beginning. Later, scientists discovered that the combination of charge and parity, CP, was also not conserved in certain decays of particles called kaons. This shook physics and earned the 1980 Nobel Prize for Val Fitch and James Cronin. This violation of symmetry means that the laws of the universe are different for matter and antimatter. And this could help explain why the universe is predominantly made of matter. This is the kind of thing that could solve great cosmic mysteries. But what is the ultimate goal of physics? For Einstein, the answer was clear. The ultimate prize was a theory of everything, a theory that unifies all fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Since Einstein's efforts in the early 1950s, physicists have been slowly moving in this direction. In the 1960s, they unified the weak force with electromagnetism. The strong nuclear force took a little more work, but in quantum chromodynamics, it also joined the party. The big challenge remains incorporating gravity, a goal that physicists have not yet fully achieved. But how do physicists create these theories of everything? This is where ideas of perfection and symmetry come in. High-energy experiments, where particles are collided at high speeds, have provided important clues. As the energies of the interactions increase, something peculiar happens. The fundamental forces begin to change their characteristics and appear the same. Electromagnetism and the weak force, for example, seem different today, but at higher energies, their distinctions fade. The electroweak theory shows that, in ancient times, when the universe was hot and young, these forces were a single force. But as the universe cooled after the Big Bang, this symmetry was broken, and the forces became distinct. Let's step back and think about this. At the beginning, the universe was perfect and symmetrical, with a superforce reigning over everything. But as it expanded and cooled, this perfect symmetry began to crack. First, gravity separated, then the strong force. The continued cooling of the universe caused the weak force to stand out from electromagnetism. Each separation was not smooth. The nature of the cosmos changed with each new separation. This symmetry breaking left deep marks on the universe. In the 1970s, physicist Alan Guth proposed that shortly after the Big Bang, the universe underwent an extremely rapid expansion, inflation. During this time, magnetic monopoles, particles with only one magnetic pole, were diluted so much that they are practically non-existent today. After inflation, the universe reheated, creating the matter we know today. However, the universe should have created as much matter as antimatter, but it seems there is much more matter. This asymmetry is one of the great unresolved mysteries. As the universe continues to cool and expand, new forces and phases may emerge, radically changing the cosmos once again. And so, the search for the theory of everything continues. Will we one day unravel all the mysteries of the universe? Leave your comment and stay tuned, because the adventure is far from over.